I'd like to welcome you to this recording in which we are going to talk about the theory of the phase lag compensator. Now, this shot actually shows the bow diagram of a phase lead compensator. In other words, this is something that we have discussed before. I'm just showing this out to perhaps point out some differences between the two compensators. Now, in the procedure for designing a phase lead compensator, we specifically use this form of the definition of a phase lead compensator. Of course, one should understand that if you have something that's not exactly the same as this, well, anything that looks like this but multiplied by some other constant or some other gain is still a phase lead compensator. The only requirement to classify a compensator as a phase lead compensator is that you should have a pole in the compensator that is larger in magnitude than the zero in the compensator. Of course, it should have the general form of a zero and a pole multiplied by a gain. But this specific form of the compensator is such that the DC gain of this compensator is 1, and we specifically selected to use this definition of the compensator with a DC gain of 1 to design our phase lead compensator. And it's clear that the DC gain is 1 from this first expression, because if we take the limit as s goes to 0, we just have 1 over 1, and of course that means that the DC gain is 1, or if we translate it into the decibel scale, it means that it's 0 decibels because the log of 1 is 0. Note that alpha is defined as the ratio between the magnitude of the pole and the magnitude of the zero. And since the pole is in magnitude larger than the zero, it means that alpha is larger than 1. And this is always true for a phase lead compensator. The time constant of the phase lead compensator, tau, is defined as the reciprocal of the pole. That is why if we write the pole and the zero in the tau s plus 1 form, we only have tau s in the denominator, but we have alpha tau s in the numerator because of the fact that the zero is smaller in magnitude than the pole. Therefore, its corresponding time constant is larger by a factor of alpha, because the pole and zero ratio is alpha. Now, if we look at the bow diagram, we see that since we use this definition at low frequencies, the bow diagram, this is now of just the compensator. Of course, we'll never use it just like this. We'll always put this in cascade with a plant and inside a feedback loop. But on its own, the bow diagram of the phase lead compensator is 0 at low frequencies, because that is so by design. That's the way we defined it. But as you increase in frequency, since the zero is smaller than the pole in magnitude, one first gets to the frequency corresponding to the zero. So that will bend upwards. And by the way, this is just the asymptotes that we see in the magnitude figure here. That will tend to bend upwards the magnitude of the bow diagram, so that it'll have a 20 decibels per decade slope, until one gets to the pole, which is now of course at a higher frequency since the pole is in magnitude larger than the zero, and then it drops the diagram down back to a zero slope, in other words, just a horizontal line. And in the phase, since we first get the zero, the effect of a zero on phase is to increase the phase. So the effect of the zero, if we come from low frequencies, is to raise the phase until the phase curve hits its maximum value at the geometric mean, and then it drops the phase. Then the effect of the pole is, of course, to then drop the phase again until it gets back to its original value that it had at low frequencies. Now, if we compare the phase lag compensator, we see that the opposite happens. And I'll speak about the vertical axis in a moment, but let's just look at the general form. Of course, in the case of a phase lag compensator, the zero is in magnitude larger than the pole. So once again, we have this definition of alpha. Note, it's the reciprocal definition of for the phase lag, because the principle that is maintained in Dorff, not all authors do it in this way, but Dorff certainly does. And even though I deviate from Dorff in the procedure for the design, in this regard, what I'm discussing now, I'm in fully agreement with Dorff. we use the symbol alpha as the ratio between the pole and the zero, or the zero and the pole, but always such that alpha is larger than zero, larger than 1. So since in the case of the phase lag, the magnitude of the zero is larger than the magnitude of the pole, the alpha is defined as z over p, as opposed to, if we go back to the phase lead, p over z, because in that case the pole was larger than 0 in magnitude. So to have alpha larger than 1, it should be p over z in the case of the phase lead, but z over p in the case of the phase lag. And so this is extremely important. If you design a phase lead or a phase lag compensator, either way, doesn't really matter, but if you design a compensator and you calculate alpha, and alpha turns out to be smaller than 1, you must immediately stop because you have an error. Alpha can never be smaller than 1. Alpha must be always larger than 1 in the lead compensator case and also in the lag compensator case. Now furthermore, we define tau in this case as the reciprocal of the 0 because it is the one that is in magnitude the largest, whereas in the case of the phase lead we define tau as 1 over the pole, or the magnitude of the pole, p. Now note that in this case it's not really valid to think of tau as a time constant. The best we can say about tau is that it's the coefficient of s when the 0 is written in the 1s plus tau form as I have it here in the bottom equation. Okay, so if we look at the bow diagram magnitude once again, and let's forget about the scales on the axis, it's horizontal initially. At very low frequencies, I have just a horizontal line until, as frequency increases, I reach the pole. Now remember, the pole is smaller than the 0 in magnitude, so I'll first reach the pole as I increase the frequency. And then the effect of the pole is to bend the magnitude bow diagram downwards in the asymptote at least, so that it will drop at 20 decibels per decade. Until at a later point in the frequency axis, as I increase the frequency, I get to the 0, and the effect of the 0 is then to bend the magnitude curve backwards or back towards a horizontal or a constant value at high frequencies. So whereas the effect of the phase lead compensator was to raise the magnitude after going through the pole and the 0, the effect of the phase lag is to drop the magnitude curve as we go through the 0 and through the pole to higher frequencies. On the other hand, if we look at the phase graph, starting at very low frequencies, at 0 frequency, we have a constant phase, and as we approach the pole, remember the pole is lower in magnitude than the 0, so we'll first reach the pole. The effect of the pole is then to drop the phase, and the phase will drop until it gets to some other minimum value, and then the effect of the 0 will kick in, and the 0 will then raise the phase again until once I've passed the 0, I'll be back at the same phase value that I had, well, quite a bit higher than the 0. I'll have the same phase as what I've started off with, namely 0. Okay, let's quickly talk about this equation. This is a new equation in edition 13, in edition 13, my apologies. In edition 13, the authors have changed its definition both for the phase and the phase lead and the phase lag compensators. And so this is the new definition that he uses in equation in edition 13, in equation 1013. I don't particularly like this definition because clearly in this definition the DC gain of the compensator is not 1 but k times alpha. If I take the limit here of s as s goes to 0, I'll be left with k alpha, and that's not 1 or 0 decibels. And because of that, I don't like this, and I'm also not going to use this equation in the procedure for designing the compensator. Actually, it's not going to be a new procedure. It's going to be exactly the same as before. I only introduced a new procedure for the phase lead compensator. The procedure for designing the phase lag compensator, I'm going to stick to exactly the procedure that was used in the 12th and earlier editions of DORF, because there DORF used a definition of the lag compensator that was such that its DC gain is 1 or 0 decibels. Let me repeat that. He used the definition of, instead of this definition, he used the definition of the lag compensator of which the DC gain is 1 or 0 decibels. But okay, let's just stay a little bit with Dorf's current definition. With this definition, of course, when S is 0, I'll have K over alpha, and of course then on the bow diagram I should have the 20 times the log base 10 of K over alpha, and that's exactly what he shows here. So at low frequencies, for this definition of the layer compensator, I'll be sitting at 10 log K alpha. Note that he's actually quite consistently used the base 10 in the log, and here he forgot to do it, so you should actually read this as log 10 K alpha. I cannot claim this as an error, but it's certainly an error if you would use this in MATLAB, or if you would simply use log in MATLAB or in Python, because that will be natural logarithm and not a log base 10. Here though is an error. In the new book, in this new figure, this minus is wrong, so you can delete the minus. This should just be 20 log K. It correctly shows on the right hand side that the difference between the low frequency and the high frequency levels of the graph is 20 log alpha. If I now on a logarithmic scale want to determine what should the low level be if the difference is 20 log alpha, of course I can write 20 log K alpha as 20 log K plus 20 log alpha because of logarithm. And so 20 log K plus 20 log alpha minus 20 log alpha will simply give you 20 log K and not minus 20 log K. So that's why I claim that the minus sign is wrong in the 13th edition, in this figure 10.6 in edition 13. Also, well, okay, I'll get back to this point in a moment. Let's just look at this general form. We see that the phase lag compensator drops the phase, and then if one realizes that to have a good relative stability as expressed with phase margin, one would like to have a maximum possible phase at the crossover frequency. From that argument, one would say, well, who in his right mind will ever use a phase lag compensator? Because it actually drops the phase, it doesn't increase the phase. Remember, in the case of the phase lead compensator, the compensator raises the phase, and we thought, well, that's wonderful because we would like to increase the phase so that we can increase the phase margin. But the phase lag compensator drops the phase, so this sounds crazy. It sounds as if one will never use something like a phase lag compensator. The point is this, however. We concede that yes, we do drop the phase, but after dropping the phase at higher frequencies, we return the phase to where it originally was. So the whole principle of the phase lag compensator is that we employ it with both the pole and the zero at such low frequencies that when we drop the phase between the pole and the zero, it doesn't really matter. It's not anywhere close to the crossover frequency. So the fact that we drop the phase there doesn't matter. It's only crucial to have the maximum phase at the frequency where the loop transfer function will drop through the 0 decibels. And of course that we cannot answer just with a compensator on its own. We must first put the compensator in the loop. In other words, we need to combine the bow diagram of the compensator with that of the plant, and then look at the resultant bow diagram. And where that bow diagram drops through 0 decibels, you don't want to mess around by reducing the phase. But we're going to place this 0 in the pole so far below that frequency that it will not actually matter that we drop the phase. And so then you may say, well, why would the lead phase lag compensator then have any effect? Well, this is the very point. It has the effect that it drops the magnitude curve by 20 log alpha at the crossover frequency. And note that at low frequencies it doesn't, well, not in this form, but in the form we'll study later on, you'll see this is 0 decibels. There, at low frequencies, it does not affect the loop transfer function bow diagram. Hence, the steady state error is not messed around in any way. But at high frequencies, we drop the loop transfer function by inserting the phase lag compensator. And in dropping the magnitude, it means that we force the loop transfer function to go through 0 decibels at a lower frequency than where it otherwise would. And normally, at lower frequencies, the loop transfer function still has, or at low frequencies, the loop transfer function has higher phase, and hence in doing so, we may actually increase the phase margin of the system because we force the magnitude curve through the 0 decibels at a lower frequency. Still quite a bit higher than the frequency corresponding to the 0, but at a lower frequency. So that is the principle on which the phase lag compensator works. So in the table at the back of chapter 10, Darvin Bishop is a little bit confusing, or makes a confusing statement by saying that if you want to increase the phase margin, you would use the phase lead compensator. And that, of course, is true. You can think of it that the phase margin is directly increased by a phase lead compensator because you add this phase at the crossover frequency. But you can, with the phase margin, also increase you can with the phase lag compensator also increase the phase margin, but not through the fact that it drops the phase, but more in an indirect way. In the way that, yes, I drop the phase at low frequencies where it doesn't matter, but then at higher frequencies, I drop the magnitude curve through 20 log alpha, and in that way, I force the overall loop transfer function magnitude curve to drop through to drop through 0 decibels. In other words, it redefines the crossover frequency at a lower frequency where the plant otherwise would have a higher phase. And in that way, in an indirect way, the phase lag compensator can also be used to increase the phase margin of the system.